When we left off the last time you guys were here, which was about 5 weeks ago, we had the following here at the bottom. We had this that we had created. We knew what the a did to the sine function, and we knew what the w did. The x is just the variable that's in there. And then we knew what h did, that was the phase shift. And this bumped it up or down depending on what the number was. This stretched it up and down. This would divide it. It would give you more maximum and minimum points between two given spots. We're going to use this in terms of the Ferris wheel. And I was going to give you a copy of the Ferris wheel and some graphs. Unfortunately, the copier in the teacher workroom has a sign on it that says, and I quote, "Sorry for the inconvenience. We will be back on Friday, March the 20th to fix it." Today's the 23rd. So I couldn't make out the mass copy, so you may have to jot some of it down. And this will keep recurring throughout the lesson. Alright, here's the opening exercise. Which graph is this? Is this A, y equals 4 sine of the quantity of x minus pi over 2, or is this B, y equals 4 cosine x? Which one is it? Before I reveal the answer, remember the graph of sine usually starts at what point? 0, 0. It usually starts at 0, 0 and then goes up and then back down and so on. And cosine generally starts where? It usually starts at 1 and then comes down and then back up. The answer is A. It should have been A. And here's why. The red dotted line on that graph is y equals 4 cosine x. If you bump this one, the blue line over, just shift this that way, this spot here will end up at 0. So it's going to be the one that had sine in it, choice A. Here is the first example. This one's going to go for a while, so get comfortable. A carnival has a Ferris wheel that is 50 feet in diameter with 12 passenger cars. When viewed from the side where passengers board, the Ferris wheel rotates counterclockwise, and that's the general form that we've been using for our Ferris wheels up to this point. Travels counterclockwise and makes 2 full turns every minute. So far you have the following important information. It has a diameter of 50 feet, it has 12 passenger cars, and it makes 2 turns in 1 minute. Riders board the Ferris wheel from a platform that is 15 feet above the ground. We will use what we have learned about periodic functions to model the position of the passenger cars from different mathematical perspectives. We will use the points on the circle in the diagram at the right, which of course you can't see yet, to represent the position of the cars on the wheel. So the diameter is 50 feet. That means from here to here is 50 feet. So the radius is 25. Remember, we've been over height and co-height before. Co-height is left to right. And if you go to the right, the co-height is positive. If you go to the left, the co-height is negative. That's why we have positive 25 here, negative 25 there. One thing we could get rid of is this while you're drawing your diagram. The negative 25 down here at the bottom, I don't think is necessary. Notice that we have the 15 feet down here that accounts for the platform where they're going to go in at. Remember all the Ferris wheels we've done before? We just did it with a diameter and a radius and whatever it was. We assumed the Ferris wheel just grazed the ground. So now we're actually going to put in the 15-foot platform at the bottom and come up with a function that takes that into account. So co-height as a function of rotation. If we started with the first car, which is in the 3 o'clock position, then we assume that to be 0 in terms of where we're starting at. But this is co-height. What is the co-height of car 1 if it's at the 3 o'clock position? How does that start out? Is it at 1? 25 feet. And then when we turn that and we go up to 90 degrees, kind of like, let's see, 90 degrees is pi over 2. Here's pi over 2. Once it gets to 90 degrees, what will the co-height be? What is the co-height when a car is on the y-axis? 0. Yeah, so it's going to go at 25 feet, and then as it's going to 90 degrees, the co-height gets to be 0. Then it's going out in the negative direction until it reaches the, what is that, the 9 o'clock position? Out there at pi. Here's what it should look like. We start up here, and I'll have to change my laser pointer to green so you can see it. There's the co-height. That's at the 3 o'clock position from the center out to car 1, 25 feet. And it makes a 90-degree turn. The co-height's now 0 because it's on the y-axis. So we turn it another 90 degrees out to 180, which is pi, and it's at negative 25. And now it's going back to the 6 o'clock position. If we're going clockwise, I was reading this off clockwise, but it works the same if you go counterclockwise. I guess this would be the noon position if we're going counterclockwise. Back to 0, and then we're back to positive 25. We have to answer this question: what is the amplitude from this graph? Can you tell what the amplitude is? We're answering the amplitude. Here is a minimum point. Here is a maximum point. What is the distance between these two? Distance is 50. Does the amplitude mean that that's 50, or is it something else? Each one. In other words, remember, the amplitude is equal to the absolute value of A. And where is A in our general form of a sinusoidal function? Remember that general form on slide 1? Where was A at? It was the very first thing. It was y equals A sine of, then you have your quantity. Now remember, when we graph these, if we had, for example, let's say a 4 sine x, what did that 4 do to the graph? Took it up to 4 and down to 4. Right, so in this case, we go up to 25 and down to 25, so what is the amplitude? The amplitude in this case would indeed be 25, and you can find the amplitude by simply doing this. Here's the distance from a max to the x-axis, or the midline if your graph is not dissected by the x-axis. Remember, you can move these graphs down and up to where they're not even passing through the x-axis. So it's the distance from a maximum point to the midline, or it's the absolute value of the distance from a minimum to the x-axis. So now we're going to deal with the height as a function of rotation. Now we're just dealing with the height of the car. So the height of car 1, and I'll draw just a little circle here so we can have something to review. Here's the circle. We're putting car 1 there. Have we taken into account the 15 feet yet? No, we have not. So the height of car 1 is how tall in terms of the problem that we're doing? We could say it's 25 feet off of the ground. Or, remember when we first started doing Ferris wheels, what did we say the height was right here? When we very first started doing it, it was 0. So here's how we could do the height function on a graph. We're going to say that we're starting at 0. Car 1 is at the 0 position, and we're just going to go up to 25 feet here, starting at 0, and it goes up to 25 feet, and then it comes back down at pi, which is 180, which means it's made a half of a turn. So now we get into negative height. It goes down to negative 25 feet at the bottom, and then back up to the starting position. There's one full rotation from here to there. This is the 90-degree position. If you're going counterclockwise, this would be at the 90-degree position. 180, 270, 360, one whole turn. What is the amplitude of this graph? 25. Here is a maximum point. We go down to the midline, which is the x-axis. It's a distance of 25. It's the same down here, but it's the absolute value of that. It's still going to be 25. So amplitude equals 25. Now we have to create equations for the height and the co-height functions. We have to create an equation for the co-height using what we've had so far. Now for the co-height function, would that be sine or cosine? He says cosine. Anybody say sine? Okay, we'll look at it. Here it is. He is right. It is cosine. It's cosine. Remember when we first started doing the Ferris wheels and we looked at cosine and sine in terms of that triangle in the first quadrant, and we figured out that on the x-axis that side was equal to cosine of theta? That's where that comes from. So we have x of theta equals, now where did the 25 come from? Why is there a 25 in there? Because it stretched, when we graphed it, it was stretched up to 25 and down to 25. And we learned that before we went on that break, that if you put a number in here, it's going to stretch it up and down that amount from the midline. So we have 25 and then cosine theta. Now what do you think the height function is going to be if the co-height function was 25 cosine theta? 25 sine theta. Excellent. Notice when we graphed the height function that it also went up to 25 and down to negative 25, so it stretched up and down 25 from the midline. And the height, when we first started doing Ferris wheels, the height of the triangle we noticed could be sine of x, and it was also in that case sine of theta. So y of theta equals 25 sine theta. Now we have to evaluate x of 0 and y of 0. And what do these mean in terms of the Ferris wheel? So if I do x of 0 for the co-height function, that would be 25 cosine of 0. Now, if you can't remember, if it's been too long over the break, you can type it in on your calculator. Cosine of 0 comes out to be what? What is cosine of 0? It comes out to be 1. So we do 25 times 1 is 25. Now 0 in terms of our Ferris wheel. Remember, we're still back at the basic starting position of 3 o'clock, which we let be 0 in terms of the degrees of movement that we've made. What does that mean if it's 0? what kind of movement have we made on the Ferris wheel? If it's 0. We've made no movement at all. Here's your Ferris wheel here. And if we've made no movement, we're still at 0 at the 3 o'clock position. And remember, this is the co-height function because it's x. So we come back with a 25. That means the co-height is 25 at that position. And does that make sense? Here's the origin. And we come over here. I'm drawing in the upper left. I'll get my laser out. Here is the origin. Co-height is 25. Does that work out according to the graph that we've made so far? Yes. All right. So what if we put in a 0 here for the height function? 25 sine of 0. What is sine of 0 on your calculator? It's 0. So I have 25 times 0. And I come back with 0. So from the starting position at 3 o'clock, which is right here, we have not moved. So if we make no movements, then the height of that car is going to be 0. So that works out as well with the graph that we've made so far. Let's evaluate pi over 2 in the co-height and the height function. Pi over 2 represents what degrees? 90, yes. Pi over 2 is 90 degrees. So let's do x of pi over 2 equals 25 times cosine of 90. Okay. Cosine of 90 degrees is what? 0. So I have 25 times 0 equals 0. So here is the Ferris wheel, and I have moved 90 degrees to this position. Is the co-height indeed 0 at that position? Yes, it is. So we know that the function we've made so far works out. Okay, for the height function, 25 times sine of 90 degrees. What is 90 degree or sine of 90 degrees? Sine of 90 degrees is what? It's 1. 25 times 1 is 25. So in our car, we started here at 0 and we've moved pi over 2 to 90. Is the height of that car 25 from the origin at that point? Yeah, so we know that our function here has worked out so far. Remember, we are building this function as we go, so we're going to change some of the ideas about this Ferris wheel and the starting point and the heights, and we're going to add things to this so that we build a function that looks like the general one that was on screen 1 when we started today. Okay, so here's where it gets interesting. We are now putting the height of the Ferris wheel above the ground into play. So down here, this 15 feet is going to come into play. The bottom of this Ferris wheel is not just barely grazing the ground. It's barely grazing the platform that you stand on to get into that car there at the bottom. So we're going to have to add 15 feet to this. So let's see what happens when we add that 15 feet into it. How will the adjusted height change the height function? And I'm going to zoom this question down. And remember the height function? It was, well, I can't do that in black. There we go. The height function was y of theta equals 25 sine of theta. How will that 15 come into play there with that function? We have plus 40 at the end, because if we're going to be adding the 15 down at the bottom, if the 15 is added at the bottom, that means that our starting position is no longer going to be 0 at the 3 o'clock position. It means that it's going to be down at the bottom. Eventually, it's going to be at the bottom since that platform is in play. So we're going to add 40 to it at the end so that we bump this up. You have a diameter of 50, that means the radius is 25. So if I add 15 more feet to that, that means whatever height I have in there is going to have to add another 15 to it. So we're going to add plus 40 at the end. At this point, the car is still in position 1, I do believe. So it's no longer just 25 at 0, it's going to be 40 feet above the ground. Here is your Ferris wheel. Here's car 1 starting there. The platform of that. So we're going to say that this is at 40 feet. Now, here's the next question. Will the co-height function change? Here's your Ferris wheel. That's 25, negative 25, positive 25. And all we need is this part here, the x-axis. Will this change? Is it not going to go to negative 25 anymore? Will it not go to positive 25 on this side? He says bump it up 40. Anybody else have a claim to make? It will not change, and here's why. Here is the Ferris wheel. I should probably go to this color. We're going left to right on this, and that Ferris wheel is not going to have a diameter that changes at all. It's still going to be 25. So your co-height is still 25 out that way and still negative 25 this way, and it creeps towards 0 there and there. We have to graph the height function, and remember the height function has changed. The height function is now y equals sine, or not sine, but it's 25 sine of theta, and then we had a plus 40 at the end of it. So let's go graph that. So if I put a plus 40 on this, how would it change what I have? Remember what we started with? It was 25 sine of theta, and it came in here. I probably should have a red marker. So yeah, it started here, and then now we're going to go up to the 40. He says we're going to go up to the 40, and then we would go back down. How far down would we go to? We have a claim that it will go up to 40. Oh, he says they'll all shift up 40. Okay, so we'll use that. Anybody have something different that they want to claim? If we put x of pi over 2 into the height function, did the height function change? Did our height, or not the height, but this is the co-height, my fault, I've misspoken. Did the co-height function change? No, it did not. Okay, so if we put in pi over 2, we would have 25 cosine of how many degrees? 90. All right, and cosine of 90 degrees is 0. So I would have 25 times 0, which is 0. So if I go up to 90 degrees, what is my co-height? 0. It's on the y-axis. So that still makes sense since the function has not changed. It means that we're at the 90-degree position, the co-height is 0, and it still works out. That function has not changed. Did our height function change? Yes, we added 40 on the end of it. So we're going to come in here and do 25 sine of pi over 2, which is 90 degrees. Then we're going to add 40 on to the end of it. So what is sine of 90 degrees? It's 1. So we come up with 25 times 1, and then we add 40. So 25 plus 40 is going to be 65. Now on the video these will be out of order, but in reality we've already gone through the graph that shows that when you go up to the maximum position, which is at the 90-degree marking on the Ferris wheel, which is this here, the height will be 65 because the platform is 15 feet off the ground, the diameter of the wheel is 50, so 50 plus 15 is indeed 65. And you can use this function to come up with that answer as well. So car 1 is going to start at 40 feet. Remember, from before, it started at 0. So now we're going to add 40 to it. And car 1 is going to start at 40 feet, since we've added 40 at the end. So he's right. Everything shifts up 40 feet. And it went up to a height of 25 before, but since we've added 40 to this, it's going up to a height of 65 there. So now we're going to say the car starts at 40 feet, which in reality is true. Diameter of 25, we add 15 for the platform, it starts at 40. So now it goes up to 65, comes back down to 40, and then it goes down to here. This is what number? 15. It goes down to 15 because the platform is 15 feet above the ground. So then it goes back up. Here is your midline right here. Remember what we said before, that it might not be possible for the midline to be other than the x-axis for the Ferris wheel, where here's an example of where it's not the x-axis. Your midline is not the x-axis. Then it goes back up and then comes back down. So this is 65 for a maximum height. Down here is a minimum height of 15. And then it goes back up to 65. Alright. So for the height as a function of amount of rotation starting at the bottom of the wheel, here is where we're going to start to change our starting point now. The starting point is no longer at 40. For the last graph that we looked at, we started at 40. That means car 1 is at the 3 o'clock position. In reality, we know when we go to the fair that you're starting off at the ground unless somebody is throwing you up to the 3 o'clock position, or you just have a trampoline to get there or whatever. So here is the platform at 50 feet, and we finally made it to reality now. You're going to get on that car at 15 feet, and you're going to go up clear to 65 feet, and then come back down to 15 feet, then back up to 65, and so on. The midline is still going to be at 40, straight across there. That puts you at the 3 o'clock position, and if you're going counterclockwise, this would be the 3 o'clock position, and then you go up to the noon position here, backwards, and then to the 9 o'clock position, back down to the 6 o'clock position. That was your starting position, and then you start all over again, back to 3 o'clock. Remember, that's in terms of a clock face.